on uniform motion. And if we just think about that word for a moment, uniform motion. Motion is pretty simple. Moving, right? Going from point A to point B in a direction. Uniform means the same or not changing, okay? So uniform motion problems are problems in which the speeds of objects is constant. So if there were two cars in the problem, you can be sure that they are both traveling at a constant speed. They might be traveling different speeds. Car A may be 70 kilometers an hour. Car B might be 100 kilometers an hour. But each car is not going to start and stop and slow down and speed up. So the problems in which the speeds of objects is constant. If you need a little bit help with that, constant means does not change. Okay? It's uniform. Now, there is a basic formula that is used for all uniform motion problems, and it includes the three variables. It includes the three aspects of anything in motion. You have the distance traveled is equal to the rate at which something travels times by the amount of time that they are traveling. So the speed that you're traveling at times the amount of time will give you the distance traveled. Quick example, let's say you're driving 40 kilometers per hour at a constant rate. You do that for 2 hours. Well, 40 kilometers per hour for 2 hours will be a distance of 80 kilometers. Okay? A nice way to remember this is in a triangle where we have our variables d here, r here, and t here. I'll explain that in a second. Basically, what it means and why it's helpful, the operation down here in between r and t is multiplication. So this reminds us that r times t is d, which we have here. But it also tells us, it just creates a fact family. R is equal to d divided by t. And t is equal to d divided by r. And in your recent practice rearranging equations, that's pretty easy for you to see. What would happen here if I divided both sides by t? Well, I'd get this same equation, the same formula, but I'd be writing it in terms of r. And I'd get r equals distance over time. So if you know the distance traveled, and you know the time it took to travel that distance, then you can just take your distance, divide it by the amount of time that you were traveling, and you'll get the speed that you were traveling. Same is true if we rewrite in terms of t. It's d over r. So go ahead and write down that fact family. Draw the triangle there. That's going to be really helpful as you're working through these uniform motion problems. And as we're working through these problems, we're going to follow a few simple steps. How to solve uniform motion problems. problems. Step 1, after you read the problem carefully, we're going to try to draw a diagram. Draw a diagram. Now, a lot of our diagrams are going to be as simple as, okay, here's a destination, this car's going this way, this car's going this way, this speed, don't draw this by the way, 70 kilometers an hour, 80 kilometers an hour, and they're both going 100 kilometers. Okay, something like that. Or, well, we'll get into what the diagrams could look like a little bit later. But we're going to draw a diagram to represent the situation. Second thing that we're going to do is set up a chart. So we're going to record information in a chart. And you'll see that when we get to it. But basically, we know that the only things involved are distance, rate, and time. So don't draw this, but basically you'll have a little chart. You'll have object number 1, object number 2. You'll have the distance that they travel. Maybe they're traveling both the same distance. Then you might have the rate that they're traveling. And for time, maybe the question is, how long does it take for them to get there, or something like that. Okay? Chart. The third thing that we're going to do is set up equations. Set up equations. Now, sometimes there's going to be one equation, sometimes there's going to be two. If it gets more challenging, sometimes there might even be 3. Okay? Step 4. Set up equation just means use these variables in algebra in order to translate the word problem into an algebra equation that we can then solve, which is, of course, step 4, solve. Okay, so we're going to be focusing on these variables. We're going to be using these steps, and before we jump into a first example, we're going to talk about a couple possible forms that a uniform motion problem can take. Okay, in your student notebook, you have a chart that looks something like this. It's going to help us discuss the different types of uniform motion problems that you might run into. I honestly can't remember why that chart is in there or what to write in that chart because I don't have my textbook or my binder at home. So I'm just going to I'm going to use the boxes to give you a couple, 3 different types that come up, okay? So in the first box, you are going to have destination there and a destination there. In this type of uniform motion problem, there are 2 objects traveling from point A to point B. And so, what do we know about them? Well, they are going the same direction. They have the same departure, and they have the same destination. So if you're thinking back to our variables, d, r, and t, they're going the same distance. Okay, but they must be going at a different rate, or they may be going at the same rate, in which case the problem's really easy, but they have a different rate of travel, and they're going to take a different amount of time to go the same distance. So here, let's just call it, if we called this, how about this, we'll call this guy number 1, and we'll call this person number 2, then you can see that in this situation, d1 equals d2. And that's going to be a huge clue for finding out, for solving this problem, because you're going to end up with 2 equations, d equals r times t and d equals r times t, and you're going to be able to set them equal to each other. Okay, that's one type of equation. Directly underneath that, you have another box, and in that one, we also have point A and point B. But this time, the objects are not traveling the same direction. One of them is going to travel from A to B, and one of them is going to travel from B to A. So again, the distance that they travel is equal. And then sometimes we actually do this problem. We say, okay, well, when are they going to pass each other? Well, let's say, hypothetically, that it ends up being here. And A only travels this far before they pass, and B travels this far before they pass. Well, then look at this. The part that A travels and the part that B travels adds up to the total distance. Okay? So this, what do we know? This has opposite, departure, and destination. Opposite, departure, and destination. And when they pass the sum of their, I'm going to use capital D just to remind you that that's going to be our variable, the sum of their distances traveled is equal to the total distance. Alright, so what does that tell us? Well, that tells us that d1, the distance that object 1 travels, d1, plus d2 is equal to the total distance. Okay? The third one I'd like to describe to you, we can put up in the top right box. And in this one, there's only one point. It's the point of departure. And object 1 and object 2 are going different directions. So in this one, you might get 2 trains and a train station, and one heads east and one heads west, and they're traveling different rates. And after 3 hours, how far apart are the trains? That kind of question, okay? So we have train 1 and train 2, and they're going in opposite directions. So 2 objects moving in opposite directions. 2 objects moving in opposite directions, and now, again, the total sum distance, let's not do that. The total distance, or let's do this. Erase that, sorry about that. The distance between the 2 objects is the sum, the distance between the 2 objects is the sum of their distances from the start point. So what does that mean? That means if we call this distance 1 and this distance 2, the amount that this guy travels is distant 1, the distance that he travels is distant 2, and the total distance between the 2 objects after a certain amount of time is simply d1 plus d2. d1 plus d2 equals d total, which is the same equation we had down here. Alright, example 1, we're going to practice following our steps. So we'll read this thing, then we'll draw a diagram, then we'll try to chart some of the things that we know, and make some equations, and then solve. So we have Frank. Frank left the ranch for town on horseback. He rode at 15 kilometers per hour. 1 hour later, his brother Jesse left the ranch and tried to catch up with Frank. Jesse rode at 20 kilometers per hour. How long did it take Jesse to catch up with Frank? Our diagram. We have a point of departure, okay? The ranch. Now it looks like the second destination is going to be town, because they're going from the ranch to town, but that's not actually the case. See if you can figure out the second point. This is where Jesse catches up to Frank. Okay? That's all that's involved in this question. We have Frank. We don't know how far they've gone. And we have Jesse. And we know that they're going to be going the exact same distance, because the problem is from the ranch to the point where they meet. Okay? Frank is traveling, we know his rate, Frank's rate is equal to 15 kilometers per hour. Jesse's rate is 20 kilometers per hour. And the question says, how long did it take Jesse to catch up with Frank? So we're on step 2, a chart. So here's what our chart might look like. We're going to have Frank and Jesse. Okay? Distance. Well, we know they're traveling the same distance, but we don't know what that distance is yet. Rate. We know that Frank is traveling 15 kilometers per hour. We know that Jesse is traveling 20 kilometers per hour. Time. We do not know the specific amount of time that either of them were traveling, but we do know that Jesse traveled for an hour less than Frank did. So let's introduce a variable. Let's let the time that Frank traveled be represented by x, in which case the time that Jesse travels is x minus 1 if we're measuring time in hours. Okay? So there we don't know the distance that each is traveling, but we do know that they're equal to each other. We do know the rate of each, and we do know the time in terms of x. Okay? Step 3, if we're doing this, 1, 2, 3. 3 is recording equations to represent the situation. So we're going to have 2 equations here, one for Frank, one for Jesse. And they're both going to be in terms of distance. And we know distance is equal, so I'm just going to use one capital D for that. And D is always R times T. So here we have the distance that Frank travels is 15 kilometers per hour for X hours. Okay? RT, rate time. The distance that Jesse travels, his rate is 20 kilometers per hour, and his time is x minus 1. Now it's very important to keep this in brackets, because otherwise you'd be something like this. And this 1, this negative 1, wouldn't be getting multiplied by the 20. So that doesn't work out, okay? So make sure that you're keeping, if it's rate times time, RT, make sure you're multiplying by all of t, right? This t is represented by x minus 1 for Jesse. All right. So now we have 2 equations. We have 1 variable, which means that we can go ahead for step 4 and we can solve this thing. Well, if we know that d equals d, and we know that d equals 15x, and d also equals 20 times x minus 1, we can say, and maybe I will just call this d1 and d2, the distance of Frank and Jesse. If d1 equals d2, then we know for certain that 15x is equal to 20x minus 1. And now we're back at our basic algebra skills, solving equations for the variable x. My first step is going to be to distribute the 20 to both terms in the binomial. Left side is not going to change. Right side, we're going to now have 20x minus 20. Now I want to get all of my x's on the same side, so I'm going to go ahead and subtract 20x from the right, and if I do that to the right, I have to do it to the left. 15 take away 20, it's going to have negative 5 x's on the left. And you might be thinking, oh, I can't have negative time, but look at what's left over here. Negative 20. So when we divide both sides by negative 5, we're going to be left with an x value of 4. Now let's go back and remember, what did x represent? X was the time that Frank was traveling. Okay? So the time that Frank is traveling is 4 hours. How long did it take? The question we need to answer is, how long did it take Jesse to catch up with Frank? They traveled the same distance. Jesse left an hour later. So the time it took Jesse to catch up is 1 hour less than Frank's travel time. Therefore, 3 hours. Okay? Again, going over the steps very carefully, we drew a diagram of what we thought was happening. We recorded our information in a chart that included both objects that are traveling, the distance they traveled, the rate at which they traveled, the time it took them to travel. We represented Jesse's time in terms of Frank's time, which was simply the variable x. From this chart, we could develop two equations. Okay, you could even say we used d1, d2, but we know that they're equal. d1, Frank's distance, 15x. d2, Jesse's distance, 20 times x minus 1. Two equations. Put it into one equation to solve it, simple algebra, and make sure you actually answered the question that was asked. How long did it take Jesse to catch up? It's 3 hours. Example 2. A plane left Montreal for Calgary, a distance of 3,000 kilometers. This plane was traveling at 550 kilometers per hour. At the same time, a plane left Calgary for Montreal, traveling at 450 kilometers per hour. How long after takeoff did the planes pass each other? So go ahead and look at the options that you have for the different types of uniform motion problems and see if you can draw the diagram. We have Calgary, Montreal. We have two airplanes, one leaving Montreal, heading for Calgary. That airplane is traveling 550 kilometers per hour. And we have an airplane going from Calgary to Montreal. That plane is traveling 450 kilometers per hour. And we're given the distance between the two cities is 3,000 kilometers. Okay, diagram done. Let's set up a table. And when we do that, so let's go 1, 2, we're going to introduce a variable, okay? We're trying to solve for how long after takeoff did the planes pass each other, okay? We're going to let x be the time from takeoff until the planes pass. Okay? We could use t, but let's use x. And we'll set up our chart. Again, we're looking for d, r, and t. And we have the two planes. So we have plane 1 from Montreal to Calgary. Plane 2 is Calgary to Montreal. Okay, and we're going to start with what we know. We're going to start with time, recorded in hours, and the time it takes for them to pass each other. They're going to be flying for the same amount of time because they left at the same time, and they're going to meet at the same time, obviously. So, and we're going to let x be the time from takeoff until the planes pass. So time for both of them is x hours. We also know the rate, And for both of them, that's given in kilometers per hour. From Montreal to Calgary, that plane is 550 kilometers per hour. From Calgary to Montreal, 450. Now, distance. We don't know how far each of these planes is going to be traveling. They might meet here, they might meet here, they might meet here, somewhere on their journey at some distance from Calgary and from Montreal. They're going to meet, but we don't know specifically what it is, but we do know that d equals r times t. So the distance that the plane from Montreal flies, we can be sure is going to be 550 kilometers per hour times x hours. And from Calgary to Montreal, that plane is going to travel this distance, 450x. All right? Now, to develop an equation, we can flip back again, look at what type of uniform motion problem this is, and there's a little note there that says the distance traveled by each of them, if you add them up, you get the total distance. Well, we know the distance between the cities is 3,000 kilometers. 3,000. And that's going to be equal to the sum of the distances of the planes. So I just put the distance that the first plane travels, add the distance that the second plane travels, and now I can solve this. I have 550 x's, 450 x's. That's on the right side, 1,000 times x. Over here I have 3,000, and I simply divide both sides by 1,000. It's going to give me a solution of x equals 3. So let's look back at what x was. X is the time from takeoff till they pass. The question is asking us how long after takeoff till they pass. So we have the right solution here. The planes pass each other 3 hours after takeoff. And there you have it. Your practice problems are listed at the bottom of page 16 there. They are from page 259, numbers 1 through 28. And basically what you're going to be doing is going to read the problem, you're going to think about the diagram, you're going to think about what information you know, what information you don't know, do you need to introduce a variable, okay? Then you're going to be looking at what type of problem is it. Are the distances equal to each other? In this case, no. But in the case of Frank and Jesse earlier, yes. Are the times equal to each other? In this case, the times were equal to each other. They were both x, but in the Frank and Jesse situation, they were different. Okay? So you're going to be coming up with those equations based on the information that you're given, and also you're going to find out what type of equation it is. Here we knew that the distance of one and the distance of the other, if we added them up, we'd get the total distance. So you're going to get those 3 types, but you're going to get variations. You're going to get certain information given, certain information not given, and it's really just figuring out what is your equation going to look like, because once you get to step 3 and you have this algebraic sentence here, the solution is pretty straightforward from there, right? So go ahead and try those out and ask if you have any questions, please.